Hey there, I will be covering the relativistic concept of simultaneity. It basically states that two different observers that are moving relative to each other will not agree on the spontaneity of an event. In order to determine whether two distant events occur simultaneously depends on the velocity of the observer. This concept really emphasizes the significance of the constant nature of the speed of light and how it affects observation in relative motion. Before I delve into the visualization and the nitty-gritty details of the concept, I would like to cover its brief history. Albert Einstein's analysis of simultaneity was shown in his special relativity paper in 1905. By an investigation utilizing the behavior of two synchronized clocks and the nature of the speed of light, he was able to uncover the relativity of simultaneity. However, this concept at first was merely a supposition. It took him several years to come up with a breakthrough. By using various thought experiments, he determined that judgment of the simultaneity of an event will vary depending on the motion of the observer. Most significant thought experiment was the synchronization of two clocks experiment. Here's how the procedure works. So suppose we have two clocks, clock A and clock B. We place the two clocks equidistant from the observer in the middle. Our main goal is to determine whether the two clocks are properly synchronized. To test this, the clock is set up so that once it hits 0 or a certain time, it will create a flash or a signal. If the observer at rest with respect to the clocks views the signal to arrive at the same moment, then the observer may make the judgment that the two clocks are synchronized. Now suppose we have a second observer in another frame of reference from the first observer. This second observer will be moving uniformly relative to clock A, in this case towards the left. So in the second observer's perspective, both the clocks and the first observer will be moving towards the right. So in the second observer's view, the signal from the clock A will have to traverse a greater distance compared to clock B. This is because the position of the first observer is moving towards the right, which is away from the signal from the clock A and towards the signal from clock B. However, the light signal still arrives to the first observer at the same moment. How is that? We have to take into account that the light postulate states that light always moves at the speed c, regardless of frame of reference. Therefore, by basing the experiment of this postulate, clock A must have signaled earlier in order for the signal to cover that greater distance, giving the second observer the assumption/judgment that the two clocks are not synchronized. Now the question is, what is the time discrepancy between the two clocks? So let's say we have this diagram, right? And we have A on the left, clock B on the right, and we have the observer in the middle. So let's say that the distance between clock A and clock B is length L. That would mean the distance between the observer and each of these clocks would be L over 2. And according to the second observer's point of view, this whole reference, right, this whole platform would be moving at a speed of v. And let's say for this case, it's moving to the right at the speed of v. We would have to find the time it takes for the signal to go from both of the clocks to the observer in the middle. So TB, the time for clock B, I would have to determine the distance it takes for the light to travel. So the distance it takes for the light to travel, let's say CTB, it would equal this total length, L over 2, for the light to go from clock B to the observer. You would have to subtract it by VTB. This is due to the fact that the observer is going towards the signal emitted by clock B. That means the length, the distance, is smaller. So now we do some algebra. C plus V times TB equals L over 2. So now we move C plus V to the other side. TB equals L over 2C plus V. Let's call that the second equation because we're going to have another one. Now we're going to have to find for A, clock A. So same process. We have to find the time it takes for the signal to go from clock A to the observer in this particular motion, right? So CTA would equal the distance, which is L over 2, plus a little bit more distance, or plus the distance it takes, L over 2 plus VTA. Now we do the same thing. We get C minus V TA equals L over 2. That means TA would equal L over 2 parentheses C minus V. Let's call that the first equation. So now we have these two equations. To find the time discrepancy, we do delta of these two. So we subtract one to the other. So let's say equation 1 minus equation 2. So TA minus TB, that would be equivalent to L over 2 parentheses C plus V minus C minus V parentheses, all of that over C minus V times C plus V. Do a bit of algebra, we get LV over C squared minus V squared, and that is the time discrepancy. So let's write it another way. So L parentheses V over C over C parentheses 1 minus V over C squared. So as you can see here, that the delta T, the time discrepancy, is very small since you have a factor of C in the denominator. There are a couple of ways to make time discrepancy to be more significant or larger. One is for the velocity v to be very large, while the other is to significantly increase the separation L between the two clocks. So there we have it. I have explained the general gist of relativistic concept of simultaneity and derived a little equation for time discrepancy. I hope this helps, and thank you for listening.